In this video, I introduce the image-based joint-embedding predictive architecture. Image-based joint-embedding predictive architecture predicts the representations of target blocks in the same image from a single context block. The self-supervised learning learns to capture the relationships between his inputs, and the objective is to assign a high energy to incompatible inputs and to assign a low energy to compatible inputs, as shown here. This is some architectures of a typical self-supervised learning method. This joint-embedding architecture, this generative architecture, and this joint-embedding predictive architecture. I-JEPA learns the embedding of a signal Y from a compatible signal X, as shown here. Given a context block in an input image, I-JEPA uses a vision transformer as a context encoder, target encoder, and a predictor to predict the representations of target blocks in the same image as shown here. This image X, this image Y. We copy and marked some of the areas. This context encoder, this target encoder, and this predictor. The targets of the predictor are the representations of image corresponding blocks in the signal Y. Input image Y is first converted into a sequence of n non-overlapping patches, which are then fed into the target encoder alpha theta bar to obtain corresponding patch level representations SY, where SY key is a representation associated with the patch key. M blocks are randomly selected from the target representations SY. BI denotes the mask corresponding to the block I as shown here, and SYI denotes the patch level representation. The target blocks are obtained by masking output of the target encoder, not the input, as shown here. This is the framework of I-JEPA model. This is the context encoder, this target encoder, and this predictor. Here is a context and target selection strategy. This original images, this context, and this four targets. A single block X is sampled as a context from the image with a random scale. Bx denotes the mask associated with the context block X. The masked context block X is fed into the context encoder F theta to obtain a patch level representations as X, as shown here. Given the output as X from a context encoder, I-JEPA predicts the M target block representations from SY1 to S1M, each corresponding to a target mask. The predictor G phi takes as input output S X of the context encoder and the positional mask token for each patch that will be predicted, and outputs a patch level prediction SY caret, where the mask tokens are parameterized by a shared learnable vector with added position embedding. The predictor is applied M times, and each time condition on the mask tokens corresponding to the target block locations, and then obtain predictions from sy caret 1 to sy caret m. The loss function is the average L2 distance between the predictions sy caret I and the target patch level representations SYI as shown here and explained in this figure. The parameters phi of the predictor and the parameters theta of the context encoder are learned through gradient-based optimization. The parameters theta bar of the target encoder are updated via exponential moving average of the context encoder parameters theta as shown here, where beta balances the phi t minus 1 and theta. Here are several examples sampled from I-JEPA, this original images, this context, and these samples from the I-JEPA model. For more details, please check with these references. Thank you. Bye.